Lab this week, it's a little bit opening up. You can do a variety of things. I would probably highly recommend doing the Diazonium reaction, which does require amino. I know a number of you got amine. And a number of you didn't. Please be prepared to do a reaction with the amine. Since I'm such a nice person, I think I'm going to provide you with some amines. Still not satisfied with the extraction process, and on Friday I actually had you do some things that maybe were not the best. Dichloromethane just was plus. So I think I'll provide you with some amine. I don't have a lot. Hopefully people that did get product won't need any. If you do get amine, I do want you to sign a sheet that says you've got some. Okay? And it will not be just set up by the balance. I will personally give you some. So if you need some, we can talk about it later. We need to get started. Any questions while I'm getting a handout out? Friedel Crafts. Friedel Crafts. Alkylation. Friedel Crafts does have some problems. Doesn't work with metadirectors. Doesn't work with anilines. Why? Well, refer back up here after you complex. It does work with other groups that have lone pairs. It does work with phenols and anisols and this type of nitrogen compound. But not with anilines. Friedel Crafts typically involves carbocation, so we need to watch out for rearrangements. This is not a problem if you want it to rearrange, but if you don't want it to rearrange, it's a potential problem. Right? For example, if you take benzene, now this maybe looks like it's supposed to be a primary carbocation. This reacts with aluminum chloride. You can envision complexing primary cation. I don't want to hardly imagine that. But these are your outcomes. It's known you get 35% of this compound where we're making the carbon-carbon bond here on the end, but you also get predominantly where the benzene is binding to the second carbon. Now again, I'm probably going to have to show a primary cation to do this. But you guys never do it, okay? Don't do what I do. Do what I say. This can complex, right? We get to this point. This can ionize and give. That's 1, 2, 3, 4. 1, 2, 3, 4. It's just we want to draw it with the same backbone. Get to that point, right? Yeah? Ooh, that's ugly, right? Primary cation, right? Yeah. I don't know any other way to show these products, unless, well, especially this one. I don't know any other way to show this one. We could get to A by maybe the benzene ring attacking the carbon and kicking off the chlorine at the same time, sort of like an SN2 type thing. Okay? Typically, you show cations when you do Friedel Crafts. But anyway, how can we get this product down here? The only way I know is to form the carbocation and then do what? And then do hydride shift. Hold on, it's not resonance. This is a new structure. And then we get this cation, right? We go from primary to secondary. And then we can attack, and off we go. You know the mechanism. I'm not going to do it, but this would give the ring binding to the second carbon, and that's actually your predominant outcome here. So always be aware of your arrangements. Now I'll label this as A because later on we will show a better way to make A. This is called a direct alkylation. It's not good. We'll show another reason after this. We'll show a better way to make A on the next page or two. So, rearrange. Another problem, and this tends to be a major problem here, unless you want it to happen. Problem's not a problem if you want it to happen, right? Polyalkylation. For example, if you take benzene and you react it with isopropyl chloride and aluminum trichloride, even though it may have shown this earlier as this being the only product, there's problems here. Because if you try to do this reaction, this will not be the only product. You'll actually get 2 groups on the ring. And it won't stop there. You'll get 3 groups on the ring. On and on and on. And you'll get multiple groups on the ring. And when you put multiple alkyl groups on the ring, that's to be called what? Polyalkylation. Multiple alkylation. Why does this happen? Well, this is good old standard line reaction, okay? Let me ask you here. Which of these, the starting material or the product, which is more reactive towards EAS reactions? Product, why? Because the product now has this alkyl group, and what does it do? What type of director or activator is it? It's a group 2, a weak activator. Okay? So the product is more reactive towards EAS. So what do we form here? This ultimately forms the carbocation, right? And we want this to react with the carbocation to make that. Well, what if the reaction is going 10%? And you have 90% of this left, and you have 10% of your product formed. I mean, it doesn't all of a sudden, boom, become that. It's okay? You build it up and you build it up. Once this starts forming, it's going to react with this preferentially over this. Because it's more reactive. What you can't do is say, okay, what do you want to call this? Isopropyl benzene? You can't say isopropyl benzene. Once we make you, we don't want you to react. It won't listen to you. It'll start coming over here and reacting. And it's more reactive than this. And what do you get? Well, what type of director is it in terms of ortho-para-meta? So I showed maybe a para product plus ortho, either way. Now which is more reactive? Starting, mono, or di? Now it's got 2. Now it's more reactive, and so it starts coming over here. And before long, this guy's like, hold on, I can't react. They won't let me react. So you'll end up with all that, and you'll have some of this left over because it just became sluggish, relatively. Question.
Is stearates eventually blocked from all carbons?
Yeah, yeah. You may be able to get them all, but probably not, especially with isopropyls. Eventually, stearates will slow it down. You may say, well, what if we just use one equivalent? Well, that's what I'm talking about here. Even if you just use one equivalent, as soon as some of this starts forming, it's going to start reacting. It doesn't matter if you only use one equivalent. Now, for example, if it puts 3 on and that's the end, and it doesn't put any more on, you can use 3 equivalents of your reactants, and you can probably make this in good yield. This is very difficult to make in good yield, unless you do some sort of tricky things. Remember, this is direct alkylation. This is a problem of direct alkylation, polyalkylation. Can anybody think of a practical way to do this and make this product in good yield other than what I've discussed? Your job is to make this in good yield to limit the polyalkylation. How would you do it? You had a question earlier. I don't know if you got it. Go ahead.
Could you sulfate first, have it as like a protecting group, and then do that, and then remove the sulfate, or the sulfate?
Okay, you're thinking. Let's see if that will work out though. You want to sulfonate first, and then do Frito-Crafts on this. Will this do Frito Craft? I'd refer to room number 1. As a metal director, you can't do Frito Crafts with that. It won't react with Frito Crafts. But it's good thinking. You maybe, and it's a metal director, if it did, it would go here. But you've got the same problem because this, with the alkyl group on, is more reactive than without the alkyl. So you really got the same problem, it's just everything is less reactive. Okay, one tricky way to make this work is use a huge amount of this. Way much more than necessary. And so even though this is more reactive, if there's just so much more of this, it maybe will be more likely to react. You can do that if you're using small molecules like benzene or toluene, because you can just use this as solvent. Okay? You can use like 0.1 mole of this, and then like 1 mole of this. Theoretical yield of this would be what? 0.1 mole. But you can't make that much of that if you only use this. So the remainder would be unreactive, and you could remove that on the rotovac because it's removable and it's cheap. So a lot of times you can get away with this and use a huge amount of this, and once this forms, there's still so much of that left. But in the end, polyalkylation is a big problem with direct alkylation. Now, we're going to move to acylation. When we move to acylation, problems 3 and 4 will not apply. But problems 1 and 2 still will. When we move to acylation, polyalkylation is not applicable, and we will see why. Okay, acylation. Acylation is a much better reaction than direct alkylation. It's going to give ketones. Here we go. Benzene. We're going to react with not an alkyl halide, but an acyl halide. And your most common is your acyl chlorides. Acyl is sort of generic for a ketone group, carbonyl group. Acyl chloride. We'll actually see acyl chlorides, also known as acid chlorides, during test 3. But our first chemistry is with them right here. This, an acid chloride, aluminum trichloride, we can get this ketone with an R group, any type of carbon group, plus HCl. R can be sp3 or sp2 carbon. It cannot be H. If it was H, it would be this. This is not a stable molecule. Because if it's H, that would be an aldehyde. A lot of times you guys like to try to make aldehydes this way. But that reagent is not stable. I'll show you a version of that a little bit later. Mechanism, very similar. The chlorine complexes to your Lewis acid, and we get this complex here. At this point, the positive chlorine will leave, just like before, and we're going to make carbocation. If this leaves, what do we get? Looks a little odd, but you get that plus that. What do you call this? Yes, this is an acylium ion. Where have we seen acylium ions? Mass spec of ketones or similar carbonyl compounds. We saw acylium ions, okay? The acylium ion is resonance stabilized. It's funny because it's on sp2 carbon. Well, it was originally sp2, but now it's sp. These electrons can come in and we can get resonance structure. The triple bond. See, this is right. This is actually a carbon's sp, correct? How many bonding regions around it? Single bond, double bond, 2 regions, linear, sp. It's actually linear at that point. I just drew it the same way it was drawn here. As soon as that leaves, this all becomes linear. And the resonance structure is also linear. Of these two, which is your major resonance structure? That one, or bonds. Okay? But we showed that stuff right there in Organic 1 when we did acylium in mass spec. So this is a way to form acylium ions in the lab in your reaction flask. Acid chlorides. And once you get your acylium, you can attack here. And so your benzene ring, these electrons attack. You don't have to move any electrons away, you just attack the plus. And off you go. So bond to carbon, there's an R there, so we just made that bond. Plus here. And it's the same thing as before. Something takes the H, we'll take the H, that chlorine from aluminum trichloride can go take the H, restore the aromaticity, and you get your final product plus HCl. Importantly, the acylium ion is not going to rearrange. Why not? Because it's resonance stabilized. It's not going to rearrange. So boom, we don't have to worry about rearrangements when we do acylation, like we have to when we do alkylation. No rearrangements. What about polyalkylation? Look here, when we react this with this to get this, which is more reactive, benzene or the product? Benzene, because the group we're putting on here is a deactivator. So is this going to react preferentially with our acylium? No. No. Acylation, you don't have any problem with polyalkylation or polyacylation. Polyacylation is not a thing in Friedel-Crafts. In fact, will the product even do a Friedel-Crafts? No. No, refer to problem number 1 on the other page. That's a matter director. Things with just matter directors will not even do Friedel-Crafts. So polyalkylation is not a problem, rearrangements is not a problem. The first 2 things on the other page is still a problem. No Friedel-Crafts can you do with a meta director, and usually anilines do not work. Now, you remember compound A that we said we were going to make later? Here's compound A. If you try to make this by direct alkylation, we got a pretty low yield, and instead it rearranged and gave another product as a major product. A better way to make compound A is to do an acylation first. This has 4 carbons on the side chain. We can do a Friedel-Crafts acylation with 4 carbons, but one of them being a ketone. Or there, here's an acid chloride. 4-carbon ketone, polyacylation is not a problem, so we get this in good yield. Then I know you're wondering, well, how do we get rid of the oxygen? Well, that can be done, and we have a new reaction here. The oxygen can be removed. What do we have to replace the oxygen with? 2 H's. Is that an oxidation or reduction? reduction. We have to reduce the oxygen off. That can be done. It can be done with hydrogen and plain old carbon, or nickel, or anything. Hydrogenation will do it. If the ketone is next to a benzene ring. But in Friedel Crafts, it already is. I mean, you make a ketone next to the benzene ring. There's actually 3 ways. Standard hydrogenation will work just like hydrogenating an alkene or an alkyne or a nitro group. Replacing oxygen with H's. There are 2 other ways. The other ways work with any ketone. And we'll actually see these down the road again. One is a mixture of zinc and HCl with mercury mixed with the zinc. What do you call something when you mix mercury with another metal? Like in a cavity, filling cavity, it used to be done. Not anymore though. An amalgam. Okay? Zinc mercury amalgam with HCl. That's called Clemmensen reduction. It's a very classical reaction for deoxygenation of carbonyl, replacing it with 2 H's. We will not look at the mechanism. This is a dissolving metal reduction. It's probably a radical reaction. The third way is Wolff-Kishner reduction. This uses hydrazine and hydroxide. The Wolff-Kishner reduction, we will look at the mechanism during test 4 material. Test 4, we will be focusing on aldehydes and ketones. And we will revisit this and we will look at the mechanism then. Okay? So really none of this are we looking at the mechanism now. The third one we will look at the mechanism at some point, but not during test 2. Your choice, any of these will remove the oxygen, replace it with 2 H's. Now you have this in good yield. It's a 2-step process. What's the process? Acylation followed by reduction. It's a much better process for getting really any alkyl group on a ring. Direct alkylation is usually kind of shied away from because of rearrangements and mainly polyalkylation. Much better way to get an alkyl side chain, 2-step route. Remember this is just your nitro reduction. One note about the aldehydes, I said that this is not stable, right? There's an old reaction out there that's in like 1 out of 10 textbooks. The reason I also want to show it is because a lot of you want to try to use this to make aldehydes with the R being an H. You actually can do it, but you can't go to the stock room and get any of this. It's not stable. But you can combine CO, which is carbon monoxide, and HCl, and they will produce that molecule in situ. What does in situ mean?
In the situation.
In the situation, in the system. Okay? That's like when you did the halogenation of sulfanilamide, your electrophilic halogen was produced in situ by combining other reagents. I mean, did you add H plus to the reaction? I plus for those who did ionization? No, I plus was generated in situ. You can do a mechanism for this. This is just combining to make that. If you draw out your Lewis structures and just use arrows to connect everything, you can show your mechanism. But what you get is an equilibrium between these two and this, and then you can get your chemistry to take place. That's called, I think, the Goderman-Hock reaction or something like that, using carbon monoxide HCl. Probably not going to find that in the textbook, though. Have to look it up on the wiki. By the way, when you put it, that would not be called an acylation. That's not an acyl group. An acyl group is typically a ketone group. What do you want to call this group? It's an aldehyde, aldehyde ketone. Ketones you call acyls. What do you call aldehydes? Formyl, like formaldehyde. So formylation. It's called the Gotterdam-Hock formylation reaction. Something like that. Okay, let's see how we did with predicting the products. You guys on the left do the first one, you guys on the right do the second one. How does that look for the first one? Chlorine complexes with the aluminum trichloride. Ionizes get you acylium. And this ring attacks the acylium. What type of director do we have? Orthopara. So I showed a para, but also ortho. Frito-Crafts does tend to give predominantly para. Yeah, I mean the fluorine's pretty small. But theoretically you're also going to get some ortho. One thing that you usually get here is, okay, we got two benzene rings. Which one is going to become substituted? I mean, this is your acyl chloride. I've seen students try to put like ketones here, stuff. Can you do an Frito-Crafts with this ring? No, it's got a meta director. You can't do Frito-Crafts with it. That's just your R group in the previous example. The R happens to be another benzene ring, but that benzene ring is not reactive here in Frito-Crafts. How about below? This is just one molecule with a Lewis acid, and I give you a big old giant hit in neon lights. Think intramolecular. Try to get the bonds drawn in there, right? Okay, 5-membered ring over there. This complexes, ionizes off, and so what do we get? We get the acylium here. What attacks it? Well, the ring. Boom. And so we get boom, 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 bond formed. Where's there an H at? Top or bottom? No, look, there's no H there. Is there an H on that carbon? No, there's one down here though. It's still there. What's up here? Yeah. See, the pi bond here goes and attacks the acylium that's hanging out over there, leaving the top carbon what? Positive. Like the pi bond went attacked, but that's positive. And there's an H down here. And then from there, the chlorine, there's from your, it's the same thing as before, take the H, restore the aromaticity. What type of director is this group? That's an sp3 carbon, ortho-para. Why does the reaction go ortho and not para? It's going to be hard to do para when, okay? It's like, okay, you want to scratch your ear, it's like, well, maybe I can do it, but this can't do it. The ortho, it attacks ortho because that group is hanging out over there, ortho. That acylium is going to be a long way from the paracarbon. It might be able to do it intermolecular, but which is faster, intra or inter? Yeah, boom. So there's a nice intramolecular, and we made a kind of a cyclic ketone. Two at the bottom. What in the world's going on down here? We got a phenol, we got this tertiary alcohol, we got some acid. What can happen here? By the end of the course, you look at a reaction and there could be like 3 or 4 things that might could happen. What type of chemical? You want to protonate this OH?
No.
Sure, let's do it. Now what do you want to do? Ionize and make a cation on the benzene ring? No, that's not good. There's nothing you can do here. There's nothing. Nothing you can do without breaking some big old rules. What else you want to do? Protonate that guy? Okay, what do you want to do now? Oh, you want it to leave here? And make what? Can we do that? Yeah, you can do that. Okay, now what do you want to do?
Attack.
You got a benzene ring that likes to attack electrophiles, especially carbocation. Okay, so we're saying, oh, almost maybe some benzene chemistry. I got an existing group. So where's the new thing going to go relative to this? Ortho-para. So see, we got to make decisions here and assess the reaction. So then we can think mechanistically as attacks here. Hopefully you can kind of realize that we're going to get bond to the tertiary carbon. We'll lose an H to put in the double bond again. You should be working these mechanisms until you can just draw products. I mean, plus what? What do you want to say also? Hey, you may also get some ortho. On a quiz or test, I probably want you to draw out the ortho. What's going on down here? Got an acid. We already know we're not going to protonate that OH because it just can't lead to anything. Alkene. Can we do anything here? This is just H plus source. This alkene. Electrons attack alkene. What do we get? Yes, good. Benzylic. Not only is it more substituted, but it's resin stabilized. Cations can be formed on the left. This is good old organic 1 alkene protonation, right? Now, can this attack cation? Yeah. So you're off. What's the product going to be? We would attack cation, bond to carbon. That carbon has a phenyl, and what else? And methyl. I mean, you should go through these mechanistically just to see. Plus what? Plus ortho, that's likely. You're going to have to purify this. Question?
That does undergo polyalkylation too. The second one, isn't that like organic one too?
Actually, both of these are alkylations. Right? Both of these are prone to doing polyalkylation. Yes, very good point. Typically, polyalkylation is not a good reaction. On the board, we can show it and understand it. In the lab, you might start getting poly. A lot of times, quizzes or tests will say assume 1 equivalent. But even 1 equivalent, you're still going to get polyalkylation, right? So you're right. There's actually a lab that's sometimes done here in Organic 2 where it is an alkylation, and you put 2 groups on. And apparently, well, you start with 2 groups already there. You do the Friedel-Crafts alkylation, you put 2 more groups on, and apparently it just stops there. So putting a 5th group is apparently not that favorable because of sterics. One time the polyalkylation is not a problem is when you're doing an internal reaction. A lot of times you can do those because only the internal reaction takes place under certain conditions. Actually, let's look at that here. Here's an example of some Friedel-Crafts. This is Tazorac, which is a medication I believe used for acne. Molecule here. That's a good looking molecule, isn't it? The recyclate ring, got an alkyne, pyridine ring. What is it? What is that over there? Ester? Yeah. How was this made? Starting material is this thiophenol. The first step is we got base. What's base going to do to this? It's like the phenol will deprotonate it. That's a pretty good nucleophile. We have this in there. It's good old SN2, right? That's good old. That's like a Williamson ether synthesis, just making a thioether. At this point, they then convert 16 to 17. And they make a ring to bond to the benzene ring. How are they doing that? Well, this is just what we looked at with the alkene. We've got an alkene, have phosphoric acid. P2O5 is just sort of dehydrated phosphoric acid. If you remove some of the water, it'll actually make your acid stronger. What is phenyl H? What is phenyl? It's a benzene ring with a substituent. If the substituent is H, what do you call the molecule? Benzene, right? Phenyl H equals phenyl. I mean, if you did this, we could abbreviate that as phenyl. But if what was coming off was H, it would be what? Yeah. Phenyl H is just a way to abbreviate benzene. It's actually using benzene as a solvent here. This is about 15 years old. I don't think they use benzene anymore much in industry. But what's happening here? This alkene becomes protonated. Are you going to make plus on Left or right? Correct. So you get carbocation there, and then the ring attacks the carbocation. Okay, you can work through that mechanism. So that's an intramolecular Friedel-Crafts alkylation, an alkyl group. And again, when you do an internal, you don't have to worry too much about polyalkylation, because the single internal reaction is going to be much faster. What type of director is the sulfur, by the way? Orthopara. So it's easy for the group to be added ortho. What are they doing next, though? 17, 18. What are they putting on 17? A methyl ketone, generically known as an acyl group. What are they using? Acid chloride. 10,4 chloride, 10,4 good buddy, is a Lewis acid. It's not as strong as like aluminum or trichloride. But 10,4 chloride is a common Lewis acid. Benzene. And so they get complexation, ionization. And so they're making the acylium ion and the ring. But let's see if the directing effects. Obviously the group goes here. Let's forget about it. If you do an EAS reaction here, where is the group going to go? Well, that's an sp3 carbon and that's a sulfur. Which one is the stronger donator? Sulfur has a lone pair. It's group 1. So group 1 directs. So it's going to go ortho-para to the sulfur. Well, this product, the new group is what? Para. Do they also get ortho? I don't know. This scheme doesn't say. Maybe it doesn't also give yield. Maybe they only get 50% yield of the para and the other is ortho. And they have to purify it out and waste a lot of money. Question?
If we take a step back to number 16, we also have a problem with not randomizing to form para and being like a 3D structure instead of having ortho.
Getting this, essentially this carbon to bond to that carbon?
Yeah.
That's going to be very difficult. If this was real long and it could come over there possibly, typically ortho is going to be the best attack for intramolecular.
Okay.
So, up to now, we've already done 2 Friedel-Crafts reactions. The rest of the chemistry is pretty advanced, and we'll probably never cover it in Organic 1 or 2. The only thing is, I believe I gave you this handout in Organic 1. What are they doing here? What does amyl lithium do to this? You got that fairly acidic SPCH there. Remember, alkynes are relatively acidic. It makes the anion, and then it complexes with the zinc. You can actually kick off a chlorine, and you can make this. That's somewhat similar to a Grignard. If that was magnesium, it would be a Grignard. It's an organometallic. From there, you can look at the chemistry if you want to look it up. It's called a Negishi reaction. The last step with the zinc, that won Nobel Prize in 2010. We'll look up the Negishi reaction. Okay. Real quickly, there was another one here. If you remember Vioxx, it's about 10 or 15 years old now, but it used to be for arthritis, but it had to be withdrawn because it was causing heart problems. It used to be $1 billion selling drug 15, 20 years ago. Here's a synthesis of Vioxx. What's the first step in the synthesis? Yeah, good old Friedel-Crafts. There are 2 reactions we'll see later on for test 4. This reaction here is just a good old SM2 that you should know already. The oxidation, we're not really going to ever do in this class. That's some standard chemistry. We'll see more of it later. I may actually give the same handout during test 4 when we refer to those other 2 reactions. Okay. You know, phenolcraft's probably one of the top 10 reactions in organic chemistry. There's about 20 or 30 top 10 reactions. Let's see where we're at, guys. Okay, we have 2 other handouts. First off, anybody not get one, a pink one from, just pass it around if you did not get one on, what is today? On Monday? Guys, I think I'm going to cover the next 2 handouts out of sequence. I think next we're going to look at benzylic chemistry, which is one that you were supposed to print out on your own. I'll just give you an introduction to this. Benzylic chemistry, we're going to start looking at the carbon over here. The other handout, we're going to go back to the ring and do the other 2 mechanisms for the ring. But right now, on this handout, we're going to look at the side chain, and first thing, benzylic. This is called benzylic carbon. We can do chemistry out here. We can do bromination, which is the first thing here. We'll start looking at multi-step synthesis. For example, get the product of this for next time. We'll also look at benzylic oxidation. And while we're doing benzylic, it's not called a benzylic nitrogen, but it is sort of the group bonded to the ring. Your anilines, we can replace this group with lots of things by what's called diazonium chemistry. The diazonium is your intermediate. And that is actually the reaction that I recommend you doing this week in lab. The diazonium reaction to replace your amine with what? An iodine. Diazonium reaction. Please be doing some reading in your textbook, here, etc. Okay, we'll hit this handout on Friday.